Hi everyone. Today we're going to continue talking about motion in the sky, but we will talk specifically about the moon, our moon. So by the end of this week, this lecture, you'll be able to explain the cycles of the moon. You'll be able to explain the far side, the near side, and also the timing, as well as describe and name the phases of the moon and why there are phase changes, and be able to determine where to look in the sky to find the rising or setting moon, depending on what phase you're at, and also compare and contrast lunar eclipses to solar eclipses. So let's think about the moon. So the moon revolves around Earth counterclockwise, this way, every month or so. However, the moon is also rotating on its own axis. So it rotates on its axis about every 27 days. So the moon moves about 13 degrees eastward every day around this orbit around Earth. And we see from Earth the portion of the moon that is lit by the sun facing us. So we never see the far side of the moon. The same side of the moon is always facing Earth, because as the moon orbits around the Earth, it's also rotating. So if we were to pretend there's a mountain on the moon, it's drawn by this pointy arrow here. And you'll notice that this pretend mountain, if we keep it in the same spot on the moon, as the moon orbits around Earth, the moon itself is also rotating on its axis. So this mountain is always pointing towards Earth. So we always see the same side of the moon. We never see the far side. So we never see the back side of the moon. Now, if you've ever heard of the dark side of the moon, there is no such thing. So there's a far side of the moon. So we never see the back side of the moon. We're always seeing the same side. But at some point, all of the moon is illuminated. So at some point in its orbit, every surface of the moon becomes illuminated. So there really is no dark side of the moon. Half the moon's always illuminated. It's just that we can only see certain amounts of that light. So you'll notice that in all of this diagram, every position of the moon, half of the moon is illuminated, and it's the half that's on the side of the sunlight. So as the sun comes in, it lights up half of the moon. So the other half is in the shadow. But we know that the moon is rotating. So as the moon itself rotates also around its axis, every bit of surface of the moon is at some point in the orbit illuminated. So dark side of the moon, not a thing. Far side of the moon, yes, that is a thing. So here is a GIF of the cycles of the moon. So different times of the month, different times of the year. You look up at the moon, we can see a different part of the moon. But you'll notice throughout all of these that we're looking at the same side of the moon. So for example, this crater is here the whole time. So we're always seeing the same side of the moon. We're just seeing a different proportion or a different percentage of that moon illuminated. So here we have the moon cycles. So a full lunar cycle is 29 and a half days for the moon to go from a new moon to a full moon to a new moon. A new moon being a moon that we cannot see because it's not at all illuminated. A full moon is fully illuminated, back to a new moon, not at all illuminated. So what's happening here is we have our Earth, we have our sun here, and we have the moon. So in this position, half of the moon is illuminated from the sun, but we can't see that half of the moon from Earth. So from Earth, all we see is the shadow side. So that is a new moon. As the moon moves a little bit around its orbit, remember it's counterclockwise, as it moves a little bit, now from Earth, we can see a bit of that sunlit part of the moon. Just a little. That is a waxing crescent. As the moon continues to rotate counterclockwise, now it's about a quarter away around its orbit, we can see about half of that illuminated side of the moon. So in this position from Earth, we can see both the dark and the light parts of the moon about half and half. That is called the first quarter moon. As the moon continues around its orbit, we will see even more of that illuminated part of the moon. So now the majority of what we can see from Earth is actually illuminated. That's a waxing gibbous. As the moon now makes its way all the way halfway around its orbit to the other side of the Earth, the whole side of the moon that we can see from Earth is illuminated. So that is a full moon. As the moon continues rotating around, then we go through the waning gibbous, the last quarter, the waning crescent, and back around to a new moon. So here we have a, just like that GIF, but now it's separated out into different pictures of the moon in the moon phases. So here the full moon is where we are seeing the entire side of the moon that is illuminated. So the whole part of the moon that's illuminated is facing Earth. So we are able to see that full illumination. As the moon is increasing in illumination, so as what we are seeing illuminated increases, we call that the waxing part of the cycle. As what we are seeing is decreasing, we call that the waning part of the cycle. So here within that, we have the crescent and the gibbous. So when we have just a sliver of moon visible, we have the crescent. So this would be a waxing crescent. And then we would have our first quarter moon, which is where we can see just half. Then we have the waxing gibbous, where we can see now even more than half. Then we have a full moon. As the moon continues around the circle, now it's going to start decreasing in the illumination that we can see. It's going to move back towards the new moon. So we would have a waning gibbous, where we can see the majority of the moon. We would have our third quarter moon, where now we can see the other half. And then we have our waning crescent, so where we just see a crescent of the moon. The next phase would be a new moon, completely dark. We wouldn't be able to see anything. So the moon cycles, I like this diagram, but it's a lot to look at, so I'm going to go through step by step. So first, let's look at, here is the sunlight. So the sun is somewhere over here on the right of our screen, and the sunlight is coming in. So if you look at the moon throughout its cycle, you will notice that the half of the moon is always illuminated. And that half of the moon is the side that's facing the sun. So it's like if you shined a flashlight on a circle, half of it would be illuminated. So no matter where the moon is in its cycle, the half of the moon facing the sun is always illuminated. So the moon facing the sun, the side of the moon that's on the side of the sun, is always going to be illuminated. So no matter where we are, it's half illuminated. So what's interesting then, or tricky, I could say, is what of that illumination are we able to see from the surface of Earth? So for example, here is a new moon. So half the moon is illuminated, but we can't see it because we are on the opposite side of the moon. So we're in alignment where we have Earth, moon, sun. So that half of the moon that's illuminated is facing the sun. All we can see is the other half of the moon that's not illuminated. So we see a new moon, or we see nothing. Now, a waxing crescent, as the moon moves along its orbit, we still have half the moon illuminated. It's the half that's facing the sunlight. But from Earth, now we can start to see a little bit of that illumination. So we see just a little bit. That is why it ends up looking like our waxing crescent. As the moon continues along, it's still illuminated halfway. Now from Earth, we can see half of the illumination and half of the darkness. So this is our view, which means it looks like this to us, a first quarter moon. As the moon continues along, now we see the majority of the illumination. So half the moon is still illuminated. It's just that now we can see almost all of that illumination. So that is a waxing gibbous. As the moon continues along, so now we are in alignment again, but the Earth is in the middle. that means we can see the full brightness of the moon. So we see the whole side of the moon that is illuminated. That is the full moon. And now it's almost the same thing in reverse. So as the moon continues along, we see less of the illumination. We see less of the illumination. We see less of the illumination. So now that we're at the waning crescent, until the moon is back in the new moon phase, where we don't see any of the illumination. So how can you tell a waning crescent from a waxing crescent? So they're both a crescent shape. However, the difference is you can tell depending what side the crescent is on. So a waxing crescent is going to be the crescent is visible on the right side, whereas the waning crescent, the crescent will be visible on the left side. So there is a difference. They're both crescent shaped, but depending on which side we're able to see, you can tell if the moon is waxing or waning. So the moon moves daily throughout the day, rises in the east, sets in the west, just like everything. It is set on our celestial sphere. However, as the moon moves relative to the sun, because the moon is not rotating around the sun, it's rotating around the earth. So the moon moves its position relative to the sun. We end up seeing different phases. But this also changes the timing of the moonrise and the moon set. So the moon is above the horizon for 50% of the day, every single day. But what changes throughout the month, depending on the phase of the moon, is what 50% that is. So is it from midnight to noon? Is it noon to midnight? Is it 6 a.m. to 6 p.m.? So the time that the moon is above the horizon is always going to be half of the day, but we don't know which half of the 24 hours it will be until we know the phase of the moon, because it is all dependent on the orientation of the moon, the sun, and the earth. So where is the moon relative to the sun? That's going to determine when we see the moon above our horizon. So let me explain that a little more. So a question like this: what time of the day would you expect a full moon to rise above the horizon? So here we have our full moon, Earth, Sun, Sun's over here. So the trick to these questions is to think about this diagram as a wheel or as a clock. So I like to think of it as a clock. So if our sun is here on the right side at, say, 3 o'clock, our full moon is exactly opposite the sun. So they are exactly opposite each other in the sky when it is a full moon. So when we are in the full moon position, the full moon, the moon, and the sun are exactly opposite of each other. So when one is rising, the other is setting. When one is setting, the other is rising. So this question says, what time of day would you expect a full moon to rise above the horizon? I would expect a full moon to rise above the horizon right exactly at sunset, when the sun is setting, because they're exactly opposite each other on the celestial sphere. So as the sun sets, the moon will rise when we're in the full moon setting, because they're opposite each other on the celestial sphere. Whenever we're in the new moon, the full moon, we have the full moon and then the earth and then the sun. Completely, the sun and the moon are in alignment on either side of the earth. So they're in opposite positions, 180 degrees from each other on that celestial sphere. So when the full moon is rising, the sun is setting. So at sunset, you would want to look in the eastern horizon to see the moon rising. So here is a diagram that, I'll be honest, it might take a couple of tries to fully understand what these diagrams are saying because there's a lot in them and they're pretty confusing. They're not intuitive as many astronomy diagrams are, but I'll try and go through step by step. So these are the locations of the moon based on the phase at sunset. So this is at sunset. Where would the moon be depending on the moon phase? So at sunset, if we were in a full moon situation, the full moon would be rising, just as we said here. They're exactly opposite each other on this celestial sphere in the full moon. So when the sun is setting in the west, it's just set below the horizon, the full moon would be rising. You'll notice that the waxing gibbous phases of the moon, the gibbous phases, are pretty opposite that of the sun, whereas the crescent phases of the moon are actually very close to the sun. So if we were at a waxing crescent moon phase, we wouldn't see the moon very much after the sun has set. So when the sun sets, the waxing crescent is close behind it because they're very close to each other in the sky. At sunset, what would be highest in the sky would be our first quarter moon. So the first quarter moon would be very high in the sky at sunset. That's because the first quarter moon is offset 90 degrees from the sun. So offset 90 degrees. So not that 180 degrees complete opposite, but it's offset by a quarter. So what time would you expect the first quarter moon to rise above the horizon? So let's go back to this one. So what time would we expect the first quarter moon to rise above the horizon? So if we think of this as a 24-hour clock, we know that the full moon and the sun would be opposites. So they're 12 hours offset from each other in terms of sunrise. So when the sun rises, 12 hours later, the full moon will rise. At that time, the sun will also be setting. So if we look at, where's my question? Here we go. If we look at the first quarter moon, when would we expect it to be rising above the horizon? I would expect it not 12 hours after the sun, but 6 hours after the sun rises. So you'd expect it to rise at 6 o'clock. So it's offset by 6 hours, by a quarter of the day from the sun. So the quarter moon is offset by 6 hours. So you would expect the quarter moon to rise at 6 o'clock a.m. So now here is the same picture, but instead of being at sunset, we are now at sunrise. So the diagram is now redrawn to look at the moon's location, depending on the phase, at the time of sunrise. So at sunrise, if we were a full moon, we know that at sunrise, we are 12 hours opposite of the full moon, completely opposite on the cycle, on the other side of the celestial sphere. So as our sun is about to rise, our full moon would be setting. And you'll notice again that the gibbous phases of the moon are close to that full moon. They are going to be setting soon as well, whereas the crescent phases of the moon are going to be closer to the sun. So the full moon is going to set at the same time as the sun rises. So the full moon is the moon that's visible all night long, but not visible during the day. So you never see a full moon when the sun is out. You always see a full moon when the sun is set, because they are on complete opposite cycles. So what time of day would this time-lapse photo have been shot? So somebody went out and took a photograph a couple of nights each month from the same location at the same time of night. What time of day would this have been? So the clue here is the full moon is the highest in the sky. So the full moon is in the middle, it's in the highest in the sky. When would the full moon be highest in the sky? We know that the full moon rises at sunset and sets at sunrise. So it's going to be the very middle of the night. So let's say it's midnight. The very middle of the night is when this photo would have been taken, or when these multiple photos would have been taken and then combined into this one really cool image. So two important concepts to know are what we call the sidereal period and the synodic period. So the sidereal period is 27.3 days. So this is the time it takes the moon to orbit around Earth and return to the same spot. So 27.3 days is what it takes for the moon to orbit around Earth and return to the same spot, the same position, relative to the celestial sphere. The synodic period is a little longer, and that is the time it takes to complete the full lunar cycle. So the full cycle of moon phases is 29.5 days. The sidereal period is the moon rotating around Earth back to the same spot. However, it takes about 2 days extra to actually complete the lunar phase cycle. Now, the key here is that the sun is also moving. So this is hard to explain in text, and I think this figure will help out. So here we have our starting position, the sun on the ecliptic. Here we have our new moon and some background stars to think about the celestial sphere. So our sun and our new moon. So after one sidereal period, our new moon has rotated around Earth, revolved around Earth, and it is back to its same position. So 27.3 days, and the moon is back to its same position. However, in those 27.3 days, the sun has shifted along the ecliptic, as it does. So in order for the moon to actually complete its full cycle of new moon to new moon, it takes another 2 days for the moon to catch up to the new position of the sun. So now, after 29.5 days, the moon has actually covered more than one revolution around the Earth, but now it has completed its full cycle, and it is back to being a new moon in between the sun and the Earth. So the difference is that the sun is also moving. So that is the key there. So if you're watching the sunset and you remember, oh my gosh, tonight is a first quarter moon, awesome. Where would you look to see the moon? It's sunset. The sun has just set. It's a first quarter moon. Where would you look? So this is where you want to think about the moon, earth, and sun like a clock. So I always think, okay, it's sunset. So how far offset is this moon phase from the sun? So here we have the sun over here, and we are talking about the first quarter moon. So they are offset by a quarter of this circle. So a quarter of a day, meaning 6 hours. So this first quarter moon would be 6 hours behind the sun. Meaning that if the sun had just set, it's about a quarter of a circle away. which means if the sun is set, that's on our horizon, that first quarter moon is going to be directly over our heads. So you would have to look straight up as you're watching the sunset to see that first quarter moon. Because the first quarter moon is going to be 6 hours offset from the sun. So it would be high in the sky at that time. So which is more common to see in the sky while the sun is out? The gibbous moons, the quarter moons, or the crescent moons? This is while the sun is out, because often you can see the moon when the sun is out. You can see the moon in the day. Which phase is the most common to see in the day with the sun? That would be the crescent moons. So that's because the crescent moons on this cycle are closest to the sun. So they aren't very far offset from the sun. So when the sun is up, the crescent moons aren't far away. So when you see the moon in the daytime, it is most likely a crescent moon. So to finish up this section on moons, let's talk about eclipses. So we have two types of eclipses. There's the lunar eclipse and the solar eclipse. The lunar eclipse is where the full moon moves through Earth's shadow. The solar eclipse is where the moon actually blocks our view of the sun. So our lunar eclipse is where the full moon actually moves through Earth's shadow. So the Earth actually blocks the light that should be illuminating the moon. So there's going to be two different sections of shadow. The umbra, which is the total complete shadow, the darkest part, and then the penumbra, which is the partial shadow. So that's larger, but it's not as dark of a shadow. So when the full moon moves into this shadow, the Earth will actually block the light that normally would be illuminating the moon. So here we have the sun, here we have the Earth, and here we have our moon in that umbra shadow. So the moon is passing through that shadow, so we're blocking the light. So the total lunar eclipse, when the moon passes into that shadow, the moon doesn't go dark, it actually turns red. It turns like a coppery, sometimes they call it a sunset moon. It turns a red color. And that's because it's not getting any direct sunlight. The only light that the moon's receiving is some indirect light that's been bent and refracted through our atmosphere. So all that's left are the red wavelengths. So the only light reaching the Earth is actually red light that has traveled through our atmosphere. So the moon will look red. So I have this great video for you guys. I have a lunar eclipse version and a solar eclipse version.
A lunar eclipse happens when the Earth blocks some or all of the sun's direct light from reaching the moon. This cosmic event only takes place during a full moon, which happens once every 29.5 days, or the length of one full orbit of the moon around the Earth. So why don't we have an eclipse every month? The moon's orbit is tilted a few degrees in relation to the Earth, so the Earth, moon, and sun don't always align. When the Earth does eclipse the sun, it casts two types of shadows on the moon. A larger shadow, known as the penumbra, and a smaller, darker shadow known as the umbra. There are three types of lunar eclipses. The first is a total lunar eclipse, when the sun, moon, and Earth are in perfect alignment and the moon falls within the Earth's umbral shadow. Total lunar eclipses are the most striking of the three types because they turn the moon a sunset red. While shorter blue wavelengths of light are scattered outward by the Earth's atmosphere, Longer red wavelengths are refracted or bent inward toward the moon, making it appear red. The brightness of the moon's red glow depends upon how much dust and clouds are in the Earth's atmosphere. Following volcanic activity, ash can block out enough light to render the moon a darker red or even near black. A partial lunar eclipse, the second type, occurs when the Earth, moon, and sun don't perfectly align, so only part of the moon passes into Earth's umbra. Earth's shadow appears very dark on the side of the moon facing Earth. Last, a penumbral lunar eclipse occurs when the moon passes through Earth's penumbral shadow. The event is so subtle that most people don't even notice. The moon will appear just slightly darker than normal. Lunar eclipses occur up to 3 times a year and can be observed from the entire nighttime half of the Earth. Unlike during a solar eclipse, it's safe to look at the moon with the naked eye during a lunar eclipse. It is only because of the distances of the sun and moon from the Earth that we are able to witness total lunar eclipses.
So next we have the solar eclipse. So now the solar eclipse, it's similar, but the moon is on the other side of the Earth. So this is where the moon is blocking our view of the sun. So remember that from the point of view of Earth, the moon and the sun have almost the same exact angular diameter. So from our point of view, they look like they take up the same amount of sky. So the moon can actually pass in front of, or that's what it looks like to us, in front of the sun and block the incoming light from the sun. So a total solar eclipse, it takes about 30 minutes for the moon to fully cover the sun, for the moon to come into full coverage. So it starts, you can see the moon in this diagram starting to move in. The moon continues moving until it's covering almost all the sun. And then as we remember, they're almost the same size to us. So the moon can almost perfectly cover that light from the sun. So if they're perfectly aligned, perfectly located, we call that a total eclipse. And at that point, we can actually see the atmosphere of the sun. So when we cover up all the light coming from, almost all the light coming from the sun, we actually see the higher atmosphere of the sun. So we can sometimes see the sun's chromosphere, which is pink. We'll learn about this later in the semester when we talk about the sun specifically, but there's pink prominences, as they're called. So during a perfectly located total eclipse, we can actually see pink on the outside of the moon. That is the sun's atmosphere. And then if it's very perfectly located, we can also see what we call the corona, which is a really pale white and extends further outwards from the sun. So there's also something that's called the diamond ring effect. So this is during a total solar eclipse when only a teeny tiny bit of the sun's surface is still visible. This is where you can see the chromosphere, so you can see the pink, you can see the corona, you can see that white kind of making the band of the diamond ring, and then still that little bit of the solar eclipse making this really beautiful figure, this really beautiful image here. This image is from NASA of this really nice diamond ring effect. So here's a similar video showing the solar eclipse. These are both from National Geographic.
A solar eclipse happens when a new moon moves between the Earth and the sun, blocking some or all of the sun's rays from reaching the Earth. By cosmic chance, even though the sun is 400 times wider than the moon, it's also 400 times farther away. Therefore, the two objects appear the same size in our sky. Astronomers are able to predict eclipses because the Earth and Moon have very predictable orbits. Why then isn't there an eclipse every month? The moon's orbit is usually tilted a few degrees north or south in relation to the Earth. When the moon does eclipse the sun, it casts two types of shadows on Earth: a smaller, darker shadow known as the umbra, and a larger shadow known as the penumbra. There are four types of solar eclipses. The first and most spectacular is a total eclipse, when the moon completely covers the sun's surface. A total eclipse can only be seen if you're standing within the umbral shadow. That's why the imaginary line created by this shadow as it races across Earth is known as the path of totality. People within the penumbral shadow see only a partial eclipse, the second type. From this view, outside the path of totality, the moon passes in front of the sun off-center, never fully covering its surface. Third, an annular eclipse occurs when the moon passes directly in front of the sun. However, unlike a total eclipse, the moon appears too small to fully cover the sun. The moon's orbit is elliptical, so sometimes it's closer to Earth and sometimes it's farther away. Last, a hybrid eclipse is when the moon's position between the Earth and sun is so finely balanced that the curvature of the Earth plays a role. The moon will be farther away from some parts of Earth along the eclipse's path, resulting in an annular eclipse. In other parts, the moon will be just close enough to fully cover the sun, resulting in a total eclipse. While a total solar eclipse happens somewhere on Earth every year or two, any given point on Earth experiences the event only about once every 400 years. We interrupt this video for an important safety announcement. Looking directly at the sun, even during an eclipse, can cause permanent eye damage. Fortunately,
Don't look directly at the sun. That's the other important thing to learn. So, how frequently do we have solar eclipses? So, in any given location, it's only once every 400 years. So, when there's a solar eclipse nearby and you have some time off, take a drive up to try and get into that path of totality. So here is the paths in the Northern Hemisphere of coming eclipses. So the next is going to be in 2024, and it's, I think it's this one. Yes. So April of 2024 is going to be the next time a path of totality crosses through the U.S. In California, we have to wait till 2045. But drive up north, have a nice vacation up there, sit in this thin path of totality, try and see the solar eclipse in 2024. So here is my final diagram to show the solar eclipse is when the moon is in between the sun and the earth. So it's blocking the sunlight in the earth from the earth. The lunar eclipse is when the earth is in between the sun and the moon, blocking the light that would normally be shining on the moon. So here is a GIF from NASA showing a solar eclipse from satellite images. So you can actually see the shadow of the moon on the earth. You can actually see that path of totality and that shadow that the moon made on the earth.